this conference. It's really wonderful to see that Poisson Geometry has now made the transition across the Atlantic and across the equator to Rio. And I want to thank Henrique and everyone else at IMPA who's worked on this to set this thing up. I know it's a significant amount of work that I haven't dared to take it on myself yet. And I think we all really appreciate what's been done. Some of you heard a talk I gave a few weeks ago in Lumini, and I apologize for the repetition that you'll hear. I tried to make it somewhat different, at least on the surface, by changing the title. I've also reduced the number of in Tutor's honor. I had 150 slides in Lumini, and I've cut it down to 16 for this talk. The title, it refers to the fact that that we try to in symplectic and Poisson geometry, that many of the interesting morphisms between our objects, whether they be Poisson manifolds or symplectic manifolds or groupoids, are not just functions, but just relations, or even something called, which I'll call hyperrelations. And I'll explain what those are as we go on. But they're poor in the sense that we can't. There are often problems with composing them. So here's a sort of summary. So here's some examples of relations that show up. And the other apology I have to make is that this may be the only page where Poisson occurs, and there will be no brackets in this talk. But I think it's related. There's so many relations between Poisson manifolds and these other structures that I hope that what I'll be saying will have more direct applications to Poisson geometry eventually. So, for example, in symplectic geometry, we have canonical relations, which are Lagrangian submanifolds of products of symplectic manifolds. And in Poisson geometry, the corresponding notion are coisotropic relations. We know that the graphs of Poisson maps are characterized by being coisotropic in the product of two Poisson manifolds. Then we have things which are not just subsets of a product, but which are things which map down to a product. So here we're getting into what I'll be calling a hyperrelation. So if we have two objects, x and y, rather than just a subset of x cross y, first being a graph of a function, next being just an arbitrary subset or submanifold or whatever, we can also talk about just some object up here which has a map down to x cross y, which is sometimes called a correspondence between x and y. Or we can also think of it as a kind of a pair of maps, one to x and one to y. But we'll see that this is, although for some purposes it's better to think of it this way, for other purposes it's better to think of it as a single map into x cross y. And sometimes it'll be even something more complicated than just a map into x cross y. Okay. So for example, Morita morphisms where x and y are Poisson manifolds, and B is a symplectic manifold with a Poisson map and an anti-Poisson map. And this anti plays an important role in this whole story, that the objects in many of our examples have kind of duals or opposites. So we change the sign of a symplectic structure or Poisson structure, and you usually dualize one side of something to be a morphism. Or another example is that the morphisms between linear spaces are a tensor product of a space with its dual. So the relations between sets form a category with a composition I'll remind you of, and this has nice properties. You can change the direction of things. You can take products. The rigidity refers to taking duals. There's a kind of transposition in which you can think of a relation between an x and y as a map in either direction. Unlike ordinary functions, you can't just reverse the direction unless it's invertible. There are various nice kinds of relations, such as smooth relations between manifolds, that don't form subcategories of the category of all relations because we can't compose them without destroying the smoothness unless we make some transversality assumptions. And the assumptions are usually assumptions on a pair of morphisms rather than on a single morphism, and that's what makes everything both difficult and interesting. So in this talk, I want to concentrate on geometric versions of this, which from the physics point of view correspond to classical mechanics, although in the background is the hope of, so to speak, quantizing all this, which is to say to find similar structures in quantum mechanics, where the objects are some kind of Hilbert spaces, and we don't know exactly what the morphism should be. There often turn out to be some kind of unbounded operators, and the composition of unbounded operators poses the same kind of problems as the composition of relations. And so I'll try to present things in a very general framework with the hope that this is the right framework in which one can then look in quantum mechanics to try to find structures that have these properties that I'll be describing. And I've said a little bit about this and written a little bit about this in talks I gave last summer in Lisbon, and you can find them either on the archive or the definitive version in the proceedings of that meeting, which is in Portugal and Matemática for more details. So as I said, I'll go soon to a general categorical setting, but I want to begin with categories of relations as the guiding example. So we'll start with sets, and a relation between two sets is just a subset of their product, and more generally a hyperrelation, which is also called a correspondence, or sometimes, and John Baez is particularly fond of this term, a span, is a diagram with something mapping into x and y, or sometimes just mapping into x cross y. And if you look at the image, if you think of it this way, then the image, which is a subset of x cross y is a relation in the usual sense. We can consider hyperrelations as morphisms, and I like to think of the morphisms as going from right to left so that the compositions, you don't have to change the order of things when you write a composition. We compose them by taking a fiber product. So if we have B going to X and Y and C going to Y and Z, then we compose them by forming their fiber product. So these are pairs, something in B and something in C, which map to the same element of Y, and then we think of that pair as giving something which takes us from Z to X via Y. This is associative. This operation is associative up to the natural isomorphisms, which is just that B cross C cross D is the same as B cross C cross D. If we make the identification of those things, then this becomes associative on the nose. The diagonal as a subset of X cross X, which we can think of as a particular hyperrelation, becomes an identity here, making them into a category. Now, I have to be a little bit more precise here, as you'll see in a minute. I glossed over something which I'll make more precise in a minute. But what we have here is that even if we have two relations, if we form their composition in this sense, it's not necessarily going to be a relation again. And I'll mention right now this kind of graphical picture that I'll use later on more. So if I have three sets, which I'll think of this way, X, Y, and Z, I can think of a relation as the elements of a relation, say from Z to Y, as being arrows going from here to here. And then a relation from y to x you might have more than one arrow coming out of a point, which is what distinguishes it from being a graph of a function. And you might have some points that don't have arrows coming out of them, for example. But what also might happen is that we can have let me do this. Let me fill these in. So suppose this is the relation G from y to z, and this is a relation F from y to x. If I compose them, I just see all the ways in which I can go to z, from z to x by following one of the G arrows and then one of the F arrows. But if I do that here, what I wind up is with I get an arrow from G to F. I'm sorry, from this point in z, from this to this point in x. But I get two different ways of getting from this point in z to this point in x. One by going through here and one by going through there. So the result, if I compose them as hyperrelations, notice there are two different arrows from here to here, and so it's really a hyperrelation, which is not a relation anymore. Although the image is simply the relation which takes this point in z to these 2 points in x, and that's all that happens. So the image of the composition is again a relation, and so we can express that in these categorical terms by saying that the composition is not always a relation, but its image is, and that's the composition on relations. And there's a functor from hyperrelations to relations, which is the image, but going back is not a functor because the composition doesn't work quite right. When does it work right? It works when given any pair of elements in one in z and one in x, and let's just talk about relations now. If there's only one, if I can get from z to x, there's only one way to get there, and then we'll call it a monic pair. Okay. Now, strictly speaking, the composition of relations is never actually a relation, because if I have two relations like this, then F is in here and G is in there, and when I compose them as hyperrelations, then what I get is something that lies in x cross y cross z, that fiber product, rather than being in x cross z where it belongs. I can project it into x cross z, and that projection will be a bijection, but it'll sort of be different as a set. And so, in fact, in order to make everything work really well, we should think of a hyperrelation as not just a diagram of B going into x and y, but an equivalence class of such diagrams up to isomorphism, where we allow a bijection here such that it makes both of these side triangles commutative. Now, a fancier way of doing all this, and something that one at some point probably does want to do, is to consider these hyperrelations as a two-category, where we don't just require isomorphisms here, but just require maps from a B to a B prime, and then we'll get some more elaborate structure. But for now, let's just think of the hyperrelations to be these diagrams up to isomorphism. So that means that we can really identify a hyperrelation with one of these diagrams, where we select we select arrows, and we tell you how many arrows there are going to be from one point in z to one point in y, for example. And you can even describe the hyperrelation as a matrix whose value is it's a y cross z, so to speak, matrix whose entries are natural numbers that tell you how many arrows there are from a point in z to a point in y. And then composition is just matrix multiplication. So here was the graphic version, but I've already given you that. So given a hyperrelation, we can call these legs the target. I call this one the target and this one the source. And it's interesting to introduce special kinds of hyperrelations, and these are already interesting in relations. We can say that the hyperrelation is injective when the target is injective. And that already, by the way, as soon as we have injectivity, it makes it a relation. It's surjective if the target is surjective. But then we have these new things that show up only for relations that are automatically satisfied for functions, which co-injectivity means that every point in y comes from at most one point in b, and co-surjective means that it comes from everything in y comes from something in b, which we can then push down into x. So co-injective and co-surjective are the properties that characterize among relations or even hyperrelations those which are the graphs of functions from y to x. Now each of these four properties passes to the image if we have happen to have a hyperrelation and we make a relation out of it. And each of these properties is closed under composition. So they define actually four subcategories of the hyperrelations. But it's most interesting to look at these in pairs, and I recently discovered some old papers from the 70s of Sergio Benente and Vladek Tulchev, where they actually already single out these two kinds, special kinds of relations. If something is surjective and co-injective, well, co-injective means that it's single-valued, but not necessarily defined everywhere, and surjective means that it's onto. So that means that x is what you could call a subquotient of y, and we'll write that by decorating the arrow from y to x at the head and call this a reduction. And Benente and Tulchev show that these are actually the things that are kind of epimorphisms in the category of relations. They speak of relations rather than hyperrelations. These are the epimorphisms, meaning that if we compose with two things on the left, you get the same result. If you take one of these and you compose with two things on the left, you get the same result only if those two things on the left were equal. So these are like epimorphisms in some categorical sense. And if we look at the same thing on the other side, injective and co-surjective means that each element of y maps to a subset of x, and these subsets are disjoint. And we call that a co-reduction. Benente and Tulchev call it a counter-reduction. And these are like monomorphisms in this category. Now, a nice property that we have is this transposition function that just interchanges x and y, something we can do with relations and hyperrelations we can't do with functions. And this exchanges all these four properties, each of these four properties with their co-properties. So that's very useful. Now, when x and y have more structure, we can consider relations that are compatible with those structures. For example, or even hyperrelations. We can talk about linear or affine, topological or smooth hyperrelations, or even symplectic and Poisson, although we have to be a little more careful when we talk about the hyperrelations, as you'll see in a minute. Then we can refine the special types. So rather than talking about injective, instead of requiring that a certain map be injective, in topology, we should require that it be properly embedded. And if it's surjective, in topology, we should say it's a surmersive, meaning that it has local cross sections. That's sort of the natural corresponding. And in the smooth case, these refinements essentially amount to first applying a tangent functor. I should probably put the word functor in quotes because we don't really yet have a category. But whenever we have a subset of x cross y, a submanifold of x cross y, we can take its tangent bundle. That's a submanifold of tx cross ty. And this going from the manifolds to their tangent bundles is compatible with composition to the extent that composition behaves nicely. And then, so for example, an embedding is a map from y to x whose tangent is also an embedding from ty to tx, and so on. When x and y are symplectic, we call a relation canonical if it's a closed Lagrangian submanifold of x cross y bar, and the bar means that we've changed the sign of the symplectic structure. And we can also deal with linear and affine symplectic relations between symplectic or affine symplectic spaces. Now, a hyperrelation isn't just a map from B to x cross y, because when we have a Lagrangian thing, B is not necessarily in general, not a symplectic manifold. So better, we have to define a hyperrelation as this kind of a diagram. For example, if we have a Lagrangian in x cross y, it's a morphism from a point to x cross y bar. But if we want a hyper thing, we shouldn't just go from a manifold to x cross y bar. What we should do is take a Lagrangian submanifold of some symplectic manifold Q, which then has a canonical relation which is a reduction to x cross y bar. So perhaps I should say, just looking at this part of the picture here, that in the symplectic case, when we have a canonical relation which is a reduction, essentially it means that the domain here is a coisotropic submanifold, and each characteristic leaf of that coisotropic submanifold goes to some point of the target, which here happens to have been a product. So this is just like symplectic reduction, almost exactly like symplectic reduction. Now we get to the main point of this talk, which is that when we have smooth relations or even smooth hyperrelations, they're not closed under composition. So just for hyperrelations, in order to be able to take the fiber product of B and C over Y, to have it again be a smooth manifold which can then map to X and Z, we need that the map from B cross C to Y cross Y, which we get by taking these two legs, should be transversal to the diagonal. And then we'll call this a transversal pair of hyperrelations. Alternatively, and this is useful when we especially don't think of the individual legs of a hyperrelation, alternatively, we can require that B cross C be transversal to X cross the diagonal of Y cross Z in X cross Y cross Y cross Z. That's the same thing of transversality. Now, for the transversal pair of smooth relations, we'll then get a smooth hyperrelation, but for it then to be a relation again, we need that when we project it into X cross Z, that this be a proper embedding. So that's the monic. Remember, that's the monic condition for a pair of hyperrelations or relations. So this is a strong version of monic because we're saying it in the smooth case. Not only is it one-to-one, not only is there only one way to get from a point to X, from a point in Z to a point in X via C and B, but that one way is sort of only one way differentiably. There's only one way to get from a tangent vector in Z to a tangent vector in X via tangent vectors to the relations C and B, and then we have this properness condition as well. In this case, we'll call B and C strongly transversal. So this is a condition that applies to relations, not to hyperrelations in general. And just a remark is that although monic makes good sense in the set theoretic setting, there doesn't seem to be a very useful notion of transversal in the set theoretic setting. So there are various important facts, namely that if we have a composition of relations, now let's say smooth relations, such that one of them is decorated at the place where they're being composed. So if this one is a a co-reduction, or if this one is a reduction, then we automatically have strong transversality. In particular, if two of them are, if both of them are, say, decorated at the tail, then we have strong transversality, and their composition is again decorated at the tail, so that we get subcategories of smooth relations. And composition of a strongly transversal pair of canonical relations is again canonical, so we get these subcategories of canonical smooth relations. And this also is true, I should say, 2' is that if we have coisotropic relations between Poisson manifolds, then their composition is, again, coisotropic. So we have these categories, but they're really too small to be interesting. Notice a canonical relation is essentially a symplectic reduction, as I said a few minutes ago. The domain is coisotropic in Y, and the fibers of what's now a map from Y to, or from this domain to X, are exactly the characteristic submanifolds of that coisotropic, or possibly discrete unions of characteristic submanifolds. As, for example, when you do symplectic reduction with respect to a non-connected Lie group, then Y would be the manifold on which the group is acting. X would be the zero level of the momentum map divided by the group. Another remark is that if we have a smooth relation between two manifolds, as it has a lift, which is essentially the conormal bundle of its graph well, I'm getting ahead of myself with WW here. It has a lift to a canonical relation between their cotangent bundles. And we haven't yet made all canonical relations into a category, which is why, but this WW is going to be the category in which they really live. And this operation is sort of functorial to the extent that all compositions are nice. Okay, so this is our sort of basic setup where we have some nice compositions, we have some nice morphisms in the smooth category, and we want to somehow be able to compose things even when they're not so nice. And now I'll go over to this more general setting in which I hope to be able to eventually find quantum analogs, and we'll do our kind of work in that setting, and then we'll apply it back to the smooth relations. So we'll just, in any category, we'll call it a special category, and there should be a better name for this, and I'm trying to think of one. I'm welcome to have suggestions. A special category is one in which we distinguish certain morphisms, and we just call those smooth. And among the pairs of morphisms, we'll distinguish certain composable pairs, and we'll call them strongly transversal. And I'll sometimes write this transversality symbol for strong transversality. And, of course, we need to have some axioms. And here's what I think of as sort of the minimal set of axioms. And all this is pretty provisional now, let me say. So first of all, we'll say we only talk about strong transversality when the things being composed are smooth, and then we require that a strongly transversal composition be again smooth. Also, if I have something smooth, then the identities on either side should be required to be strongly transversal to it. In particular, they're smooth. And then we'll say X and Y are smooth objects. So not every object is smooth. And finally, if we have a composable pair, and if one is smooth and the other is not just an identity, but a smooth isomorphism, then we have strong transversality. So, for example, this applies to the examples above, where the objects could be all sets, but we only say a map is smooth if it's a a smooth map between smooth manifolds. So the only smooth objects would be the smooth manifolds. But another example, which is kind of goes a little above sets, is symplectic manifolds and canonical relations. Because we can have the same set be a symplectic manifold in two different ways, and we want to consider those as different objects in the category. So then the category would be the one whose objects are symplectic manifolds, specifically, whose morphisms are all relations between them, but for which the smooth relations are only the canonical relations. And then strong transversality is what we said it was before. And then there's this property that holds in these examples, which I don't need for some of the things I'm going to do, but seems like it should be useful to impose, which is that if we have three morphisms, and if when we try to compose the three of them by, say, first composing F and G to get something smooth and then composing with H, if those are both strongly transversal, so that we could say we have a strongly transversal triple, then if we tried doing the composition the other way, it would also have been strongly transversal. So this seems like a nice condition. It's a kind of associativity that we don't need to seem to need to impose, but it might be nice for some things that I haven't yet thought of. So when the identity is when the identity of some object is smooth, as I said, we'll call it a smooth object. And a special functor between special categories is one which preserves smoothness and strong transversality. So, for example, in all relations, we can just say everything's smooth and everything's strongly transversal. That's a special category. Not very interesting. Or we can take all relations, but only monic pairs, call those strongly transversal. And that seems to be already seems to be something interesting. And smooth, but with the definition above, canonical relations or coisotropic between Poisson manifolds, or smooth hyperrelations in which we declare transversal pairs to be strongly transversal, because we know we can compose those nicely and get something smooth. It'll still be a hyperrelation. Or canonical hyperrelations, as I described before, where we do this. T star seems to be a kind of special, well, actually, that's, I think I was wrong already. I'm wrong in the definition of a special functor, because if we go from all relations between manifolds, there is no T star applied to general relations. So we only would want to take T star of something that's smooth. So a special functor isn't really a functor anymore between the categories. So anyway, let's go on. So this is the main construction, and the WW stands for Katrine Verheim and Chris Woodward, who carried out this construction for canonical relations. They wanted to make the canonical relations into a category so that they could quantize it, not in the usual terms of quantum mechanics into Hilbert spaces, but into a much more elaborate quantization involving Floer homology. And what they wanted to do was to show that when they attached Floer homology groups to certain symplectic manifolds, that when you had a canonical relation, you could carry Floer theory from one manifold to another. And they actually carried this out, and it's beautiful work. And most of it is very technical theory of pseudo-holomorphic curves, which which is not a part of what I've been doing. I've been just concentrating on the easy part, which is the formal constructions on the symplectic side. So here's how we're going to do what we're going to do. We're going to start with a special category, and you should think of smooth relations or canonical relations. And we're going to build up a bigger category in which we're now allowed to carry out all the compositions we want in such a way that if a composition was strongly transversal, it stays what it was before. And I like to think of this thing nowadays as kind of dynamical. So what we'll do is we'll start with our category C, and we'll start with paths. So what's a path? It's just an infinite diagram of morphisms which can be composed, but where all but finitely many of them are identity morphisms. So it's like compactly supported. And after doing this, it's occurred to me that this is a little bit like the process where we go from a Lie algebroid to a groupoid by first starting with paths and then introducing some kind of a homotopy. So the individual morphisms are kind of like we almost think of them as like the infinitesimals in a Lie algebroid. And so this is a little bit like maybe very superficially, although it would be nice if there were more deep connections possible. It's superficially a bit like the Kreinig-Fernandes or the Cattaneo-Felder constructions of groupoids out of their Lie algebroids by starting with paths and then passing to a quotient. So why do we want finitely many of these? Well, okay. So these are the paths. So two paths are going to be equivalent if we allow ourselves the following two kinds of moves. First of all, we can just throw in identity morphisms anywhere. Just finitely many. Although if you wanted to throw in infinitely many in these infinite tails, it wouldn't make much difference. But let's just not do that. So this is kind of like reparametrization. If you follow a path and then you allow yourself to sit for a while somewhere by an identity, we're going to allow that in either direction. But the more serious thing is that if somewhere along a path we have a strongly transversal pair, then we'll allow ourselves to replace this by its composition. And just to keep the indexing the same, it's handy to throw in an identity morphism in one of the two places so that we don't have to change what was going on far away. We don't have to renumber anything when we do this kind of a replacement. So we now look at the equivalence classes of paths, and such an equivalence class of paths, the following things are all well defined. First of all, there's a target, because after a while these are all identity maps, so they're all between the same space. And so there's a target, which we can call X, and a source, which we'll call Y. So suppose I have two of these that match up, and I want to compose them. So here's where we use our this is the high-tech part of this talk. We want to compose them. They're too big to fit on the page, so we first shrink one. And then we put the other one beside it. So now we go from, now we have two Y's here, so I just consolidate those, and we can have a few. We had infinitely many Y's here and here, so we can forget about having infinitely many. We can just keep a few of them if we want. And now we have a morphism from X to Z. That's pretty clearly associative. The units are the morphisms of which every arrow is an identity. Okay. So that makes a category. That gives us a category which I'll call WW of C. It's the Verheim-Woodward category constructed out of C. And original morphisms can be kind of embedded in here as the paths in which there's one non-identity arrow, and everything on both sides of it is an identity arrow. There's also a functor that, so we embed C in WWC, but it's not really a functor because C wasn't a I'm sorry, we can embed the smooth morphisms of C into WWC. I should have said that in these paths, we only looked at paths of smooth morphisms. And so we can embed the smooth morphisms back into WWC, but these weren't a category, so we can't say it was a functor. However, there is a functor in the other way, which takes a path and simply composes all the morphisms in the path. And since after a while we just have identities, the fact that there were infinitely many doesn't get in the way. And so it's a kind of a scattering operator. If you think of this path as a process, you can have something coming in from the right, my right, from something coming in from y at minus infinity. Or I guess the order is the wrong way. Something coming in at infinity and going to minus infinity. And that's kind of like a scattering operator. And the existence of this composition shows that when we take a morphism in C, different morphisms in C and put them in this WWC, even though we've allowed these equivalence relations, we don't lose any information because we get back to here by this composition functor. So that's this cross-section here. And there's actually a kind of universal property in that if we have any other category, D, and if I have something that takes smooth morphisms in here, which takes strongly transversal compositions to compositions in the category D, then it always factors through here. And in fact, that sort of characterizes this WWC. And it's a little bit like, it's a little bit like characterizing the groupoid of a Lie algebroid by saying whenever we have a map of a Lie algebroid into the Lie algebroid of a groupoid, then that lifts to the integrating groupoid. Okay. Now, special isn't good enough for some purposes. We need extra special. And I think I'm going to have to speed up a little here. We'll say it's extra special if it has these very nice morphisms which allow strong transversality. So if every smooth isomorphism is isomorphism, both a reduction and a co-reduction, and if a composition is strongly transversal, if one of the morphisms is decorated at y, and finally, and this is the new thing, every smooth morphism can be factored as a strongly transversal product of a co-reduction followed by a reduction. And it was already observed by, it was already observed, this is essentially already observed by Tolchev and Benenti at least for linear canonical relations. So, for example, this category of canonical relations, we take all relations between symplectic manifolds, it's extra special with the smooth morphisms being canonical relations, reductions and co-reductions. I'll tell you later what the factorization is. And also relations between manifolds in the same way. Hyperrelations between manifolds with reductions being those for which the target leg is a submersion, co-reductions those for which rho is a submersion. And the factorization here is the following. And here, this is the first place where we introduce this notion of a graph. So if I have a map from B to X, or even more generally, a relation from B to X, I can think of its graph as a relation from a point to x cross b. And then I can build the factorization of a general hyperrelation as hyperrelations by first taking y and putting it in here, and then taking a point that I kind of think of being next to y and putting it in as the graph of the lambda leg. And then I go from here back to x by projecting onto x, but also projecting b cross y onto a point by taking the graph of rho, but not rho, but the graph of rho transpose, because I have to change the order of b and y. The graph of rho would be in y cross b. I want the graph of it. So you can check that this factorization works. That this is this is injective. This is a co-reduction. This is a reduction, and it's strongly transversal. So here's the first result, which kind of is part of my justification for introducing all this terminology, is that if we have an extra special category, then any morphism, which you remember is an equivalence class of paths, can be represented by a path in which there are only two non-identity morphisms. And the first one of them is a co-reduction, and the second one is reduction. So this, I think of this as a simplification result, and which I hope can simplify things that you want to do with these categories built out of a priori badly composable morphisms. Okay, so for the next result, we have to even go a little further in terms of our categorical structure. Not just an extra special category, but an extra special rigid monoidal category. So what do these terms mean? Monoidal means that we can form products. So in almost all the cases, the examples I've given, the product is just a Cartesian product. However, in linear, on the quantum side, when we rather than taking Cartesian products, we'll want to take tensor products. But if we're dealing with linear canonical relations, it's still Cartesian products. And physically, these products usually represent some kind of coupling of systems. But we also have a notion of dual, so that the morphisms from y to x can also be thought of as morphisms from a point into x cross the dual of y. And so just think of the category of think of C as S-rel, where these are relations between symplectic manifolds. The product is the usual product. The dual is change the sign of the symplectic structure. Or we could take Poisson manifolds and change the sign of the symplectic structure. And then the smooth morphisms are going to be the coisotropic relations. Then we have the following theorem that that instead of thinking of morphisms as of WWC as being these paths, we can actually think of them as I guess a better term would be canonical hyperrelations. So there are going to be morphisms like this, where we go from a point. What's a point, by the way? Oh, in a monoidal category, I said we have a product. There's also a unit for that product. There's something whose product with anything is that thing itself. And in our examples, it's just a set containing one point. In vector spaces with tensor product, it would be the ground field. So this would be a hypercanonical relation. I should say it's a hypermorphism, probably. It's a hypermorphism where this one is a co-reduction, this is a reduction. And here's composition. Composition becomes really trivial. Remember, a special category, we made composition trivial just by taking paths. We just put things next to one another. Here, to compose these hyperrelations, what we do to compose them is we just do a kind of exterior composition where we take a Cartesian product. If we had two hyperrelations, rather than taking the fiber product, in other words, rather than just taking the points in here and taking the fiber product before projecting it to x cross z, here we just look at the whole product, but we think of it going now from a point to q cross q prime, and we think of going into x cross z by this composition of two this composition of two co-reductions. So what I omitted telling you here, I didn't say exactly what an extra special rigid monoidal category was, but in a rigid monoidal category, we have these special morphisms for any object. One goes from a point to x cross x bar, and that's the diagonal morphism. And then there's a kind of co-diagonal, which is sometimes called a trace, which is what it is in vector spaces, from x bar cross x to a point. So this is part of the structure of a rigid monoidal category, and in our extra special situation, we require that these things are decorated. And this thing here is going to be the co-diagonal of y crossed with the identity maps of x and z bar. And part of the axioms will be require that that thing again be a reduction. So those are the main things I have to say, except later I want to say something about how we can keep track of the bad compositions when we pass to these categories. So the general theme is we have these categories. We have these nice smooth objects. We try to compose them. Sometimes the result isn't smooth. So we do a trick in order to be able to compose everything so we can still use a categorical language. But then we want to keep track of what we lost by allowing ourselves to make these compositions. And that'll be sort of the last part of the talk. But let me just say a few words about how we first of all, the simplification. So in the category C, and so we do need this extra structure actually for theorem 1 already. We have these morphisms from this diagonal and co-diagonal. Any morphism has a graph. Now, this is not an assumption. We can actually build this graph by taking a strongly transversal composition, first going from a point to y cross y bar, and then just applying the morphism L on the first factor and the identity on the second factor. So this should just be L cross the identity of y. So I should have said that for theorem 1 we already need this monoidal structure, which we have in the categories that we started being interested in. Then there's this strongly transversal factorization of a map through its graph. So if you think about just ordinary maps or even relations, for ordinary maps you just go through x cross y. But because we're dealing with relations and maybe things like canonical relations, the ordinary graph isn't a good thing in our category. We have to throw in this extra factor of y bar in the middle. And then we go into y by taking y to itself, but also taking a point into the graph, and then we come back down by the identity cross epsilon. So you saw something, I showed you something like this before. So So this is the lowest case of theorem 1, which says that any any chain of morphisms can be factored into a product of 2. So here I seem to be going in the wrong direction. I'm taking a chain of 1 and factoring it. But let's look at a longer one. Suppose we have 4 things, and we want to write it as a product of 2. So we'll think of this as a path. There's really infinitely many units to the left and right, but we don't need to write those in. So how are we going to write this as a product of just 2? Well, first of all, we'll factor each one by using the factorization, which is actually part of the structure that we need. So this is actually part of the structure of an extra special rigid monoidal category. And now remember that we have these decorations here in the factorization. And because we have decoration at x3, I won't even label the objects here, but there's just some objects here. Remember, this is a product of 3 things. So these are going to get, these objects get bigger and bigger. Because we have decoration here, I can go across here, and this product here will be equal to this in the WW category. Similarly, I can cut across these corners here, and so this original chain of 4 things has now become a chain of 1, 2, 3, 4, 5. So we're not getting closer to 2 yet, but we can now repeat the process, and I will leave off most of the decorations except the ones here, which I'll need in a minute, and cut across again, and do it again, and cut across again, and do it one more time. And let's just put on the decorations on the tails here and the heads here. And now notice that along this lower right-hand side, we have all co-reductions, so we can compose them to get a single co-reduction. On this side, we have all reductions, and we can compose them to get a single reduction. And now we've written the original chain as a product of a co-reduction and a reduction. And all these moves are legitimate within this WW category. Here, in going from this chain to this, I actually, you should really do it 2 steps, a step at a time. But basically, this is a proof of that first factorization theorem in the case n equals 4, but it's the same in the general case. When I gave a talk, I have the feeling this argument should be somewhere else. And when I gave a talk at NYU in the spring, Sylvan Capel thought that this is somehow related to something that J.C. Whitehead did many, many years ago in simple homotopy theory. But it seems to be a little different from that. Okay. Theorem 2, just a word is that the idea of a hyperlagrangian came from the exposition of Gilman and Sternberg of the theory of generating functions for Lagrangian submanifolds of a cotangent bundle, in which they get these things by taking a Lagrangian submanifold in a bigger cotangent bundle and reducing it to the cotangent bundle of P. That's essentially a way of looking at the theory of generating functions. And Benente and Tulchev, and especially Benente in a recent book, a big book manuscript, which you can find on his webpage, uses similar ideas. And the idea is that you can't necessarily, you can try to do a composition of generating functions, and sometimes you run into this bad composition problem. And what Benente remarks is that rather than trying to do the bad composition, just leave it as one of these big hyper Lagrangian things, and you can do some interesting things with that. Roughly a generating family, to get something in cotangent bundle of P, you take a function on B, that gives you something in T star of B, and then you push it down to T star of P by T star of some submersion from B to P. I think I'll go a little quicker now. So as I said, to go from WW to HL, this is hyper-Lagrangians or hyper-relations in more general, we associate to each generator in the original category its graph. And then we can do compositions in the kind of brutal way, and then we can show by an argument that this compositions are nice. Going the other way, you assign to every graph a morphism by a diagram like this. So the last thing, just do I have 1 minute, 2 minutes? I want to talk about how poor relations can be, or more precisely, how bad the compositions can be. And it could be measured by, in linear cases, we can measure it by things called defects and co-defects. And I will make these slides available so that people can look at in more details. But I wanted to skip ahead to something that I really didn't have when I talked in Lumini, which is the notion of trajectories, which I think is an interesting idea with which I want to close. And this applies for general relations or even hyperrelations. And so given a path, remember the morphisms in the WW category, these paths of morphisms in the original one, given a path, but now this is specific for relations, if we want to keep track of how non-monic the compositions were, this is what I'm going to be concentrating on here, we can look at trajectories. So what's a trajectory for a path of relations? It's a sequence of points in these sets, or manifolds, or whatever, such that each pair is in one of the relations in the path. We can also consider it as a sequence of pairs, which then makes sense in a hyperrelation. And let me see if I have the graphical picture. But we can look at the space of all trajectories. And we can look at the space of all trajectories, which are all the ways of getting from some point in the source y to the target x. And if we want to keep track of how bad the compositions were, we want to look at the space of all trajectories and map it to x cross y, where the image is just that composition, the result of that composition functor from the WW category into the original category. And the fibers of this map from the space of all paths to the space of the endpoints of the paths kind of measure the total badness of the compositions. And we can show that this is invariant under those moves that were allowed in forming the WW category. So the fiber of this forms a kind of total badness of the compositions. And these trajectories, if we think of the relations in that graphical sense, then the trajectories are really just paths through this family of remember, if we think of the relations as a kind of giving a kind of directed graph, then they're just paths through this graph. So just to end with some questions, is there some notion of trajectory in other categories other than just relations, like in particular on the quantum side? And to what extent do these trajectory spaces classify the WW morphisms? So I will end with those questions, and I'm happy to have your questions. And with both apology, only partial apology for the sort of half-bakedness of these ideas, I hope that they will be inspiring for some of you, as they will be for me, to try to work out in some details for what I think is an interesting way to understand the limitations of composition in certain very interesting categories. Thanks.